Good morning, everybody. Welcome to our virtual Tech Takeover series. Boy, has time changed in a mere 3 months for everybody around the world. This is really fantastic what's happening. Thank you for joining us. What I'll start with is, I haven't talked to our members. I haven't talked to you guys. I don't know who's on the call. I know it's a lot. But what I want to share with you is all of us are experiencing this rapid transformation that is happening because of this COVID pandemic. And you're seeing that digitization, all the things we talk about at Automation Alley around our Industry 4.0 Knowledge Center, talking about how we have to embrace not just the things we know how to do physically in our manufacturing plants, but the digital that overlays that. It's all going to get accelerated very, very quickly. And so the session we have today, I think, is one of those ones that you really need to pay attention to. When I met Luke Tuttle, who's the Chief Operating Officer, and he'll be talking next, with Ready Robotics. I met him in New York City. We were at a World Economic Forum event around the future of production. And we were at a strategy session. And Luke explained to me what Ready Robotics does and is. And it was almost incredulous because he talked about how you could use any robot, you could program it, you didn't need to know how to program. And I thought, this has potential. Well, then I sat with Luke and I saw what's possible. And everybody needs to pay attention to this because what happens in Michigan is we were the first to use robots around the world, right? The auto industry back in the 60s and 70s, we dominate robots. But because of that, it's actually a little bit of an Achilles heel for us because we think we understand what's possible. We think we have a knowledge that is superior to everyone around the world. And what's happening is, as software meets the physical, which is a robot, the world is changing. So we need to pay attention to what's possible. And Luke and his team at Ready Robotics, they have a gee whiz, wow, what's possible solution. So I want y'all to pay attention today. Have a great session. I wish I could be with you in person. We're desperate for the days that we can do them back in our facility. But you guys have a great day. I have to jump off on another meeting. But Luke, I'm going to turn it over to you and have a great session today.
That's great. Thank you, Tom, for the excellent introduction. And we're extremely happy to be here with Automation Alley today. As Tom said, we met a few months ago and came together to be able to present this webinar. So today, all right, thank you, Tom, much appreciated. So today we've got a great agenda with a few slides to start. The most exciting piece is going to be 2 demos done by Kel Garen, our CTO, that shows you exactly how you can program some tasks on your own in your facility. And we'll take you through those processes end to end and show you exactly how that can be done. So with that, I'm going to pass over to Eric Bjornyard, our VP of Marketing. He's going to lead the deck in the start, and I'll talk to you soon in a few minutes.
Awesome. Thanks, Luke. All right, let me share my screen here, guys. And you should be looking at a slide that says how to deploy robotic automation on your own. Can everybody see that? All right, perfect. So I'll dive in. So really quickly, thanks for joining us today. We're super excited to present on how any manufacturer, literally any manufacturer, can automate on their own with no external support and no robotics experience needed. The presenters today, so Kel was mentioned. Kel is co-founder of Ready, PhD in robotics, multiple patents related to software for human robot interaction. Luke is a humble technology executive who's led and scaled engineering and product teams for global leaders and pioneers in robotics, fintech, ad tech, and CRM. And I've had the pleasure of growing multiple SaaS startups into market leaders. And so now for the first time in my career, I'm excited to be building something that I feel like truly matters to the world. So really quick bit of background on Ready. Our mission is to improve the world's quality of life and productivity through automation. So we're a robotic software startup based in Columbus, Ohio. We don't make robots, we make robotic software. We're located here intentionally. We wanted to be a short drive away from about 60% of US manufacturing. And we started Ready because robots are very difficult to program. This makes automation far harder and more expensive than it needs to be, which is why we're championing user-friendly robotic programming. The premise is, by making robots easy to program, we're making automation accessible to all manufacturers, regardless of size, vertical, robotics, or automation experience. So Luke was kind of alluding to the agenda. He'll run through manufacturing and automation challenges that are limiting the adoption of robotic automation. He'll introduce everybody to no-code programming, which we think is going to be pretty powerful and change the industry. We've got a few really interesting demos that Kel has done and we'll walk you through. Those are really quick programming tasks. You'll see how quick and easy it is to actually program robots using no-code programming. And then I'll walk through a couple real-world use cases, submit questions as we go. Our plan is to kind of come back to questions at the end. But if something piques your curiosity or question arises, please submit your questions as we go along. And without further ado, I'll kick it back over to Luke.
Great, thank you, Eric. So just to frame some of the conversation, and what we're showing here is what many of you have experienced, that in manufacturing, there's a high need to be responsive to how consumers want to buy goods today, which is they like personalization, they want specialized products, and what's that resulted in is this very large growth in products. The impact of that for manufacturing is that the runs are shorter, there's a high degree of changeover, there's more complexity in the work, and the economies of scale have gone down. And what that means is that the days of being an invest in some sort of product line that's going to produce a good for a long period of time are over. And we need the ability to be more flexible, responsive to both demand, as well as, again, this need to be able to produce individual specialized parts. Next slide, please, Eric. And we've all been impacted by COVID as well. From a perspective, just the impact on the health and safety of our employees, which is always first in mind, that we're able to have safe workplaces. But it also has highlighted some of the dependencies within our supply chain. Some of those were geographic. Some of those were due to specific suppliers of a good. And also the inability to scale due to fluctuating demand for different types of products driven by this new situation that had occurred. So we have a white paper that discusses these in detail, but this is something that we need to think about how we can address ongoing, because this isn't necessarily just a black swan event when it comes to COVID-19, but a problem that can occur for any number of reasons for that we need to address. Next slide, please, Eric. And a problem that we were addressing even before the current crisis, and one of the reasons we believe so strongly in making automation more accessible, is this challenge in skilled labor. And this is something that, as Tom mentioned, that we met at a World Economic Forum event, where one of the large topics of conversation was in training and upskilling, reskilling, the ways to engage and find new people in the manufacturing workforce. And we feel that those problems still exist despite large unemployment right now. So there's dramatic unemployment rates, but that hasn't changed the fact that there are workers who are able to participate in this advanced manufacturing environment. Very specifically, it comes down to being able to program robots. There's a large barrier in getting access to the kind of training that you need to program those today. Robots don't exist in a vacuum. There are also logic controllers that exist in the work cells that have their own languages, and there's a large amount of vendors that provide those. And the skills between vendors aren't always necessarily transferable. So it's not very easy necessarily to find somebody that knows one brand and immediately have them be productive in another. So this is yet another reason that we're trying to solve this problem of complexity in automation. And again, even on the right-hand side is, again, despite unemployment, the turnover has already been high as well, that there's a constant cycle of folks coming into the workforce and choosing to leave for a variety of reasons, and being able to train and have them be very productive quickly when you bring in new staff into your factories. So one of the problems I alluded to there is the training necessary for programming robots. And one of the pieces that make that challenging is there's over 70 robot brands. There's about 10 that dominate the industry, but there's still many of these brands in use, and they all have a different interface. So these are the what are called the teach pendants that are used to program a robot. Some are touchscreen, as the one from Universal Robots on the left. Others have these keypads. A wide variety of interaction styles with menus or writing programming code. But this is a large barrier to any individual to be able to operate a robot because of the complexity and uniquenesses that these interfaces have. And then when it comes to training, we've shown some of the courses outlined by some of the major vendors to go through, or what the course curriculum is, so that you can become proficient in basic tasks. So of course, to become an expert, you generally need some number of hours of repetition and work in that space. But even to get started, it requires some of this training, and some of this training required on-site participation at either a vendor's or one of their partners' locations. Some of it can be done online, but as you can see, there's a wide variety of ways that vendors even approach training, but it requires a number of courses that themselves cost money. It costs time and time away from work for that employee, and also many times travel costs. So these costs can add up to thousands of dollars just to be able to do basic interactions with the robot. And not only from a people perspective, there are many of you use integrators to do work within your factories. And it's very useful when you've got a project that you need to get done quickly. But even the skilled integrators are scarce. They themselves are also grappling with some of this problem with staffing, choosing which brands to invest in themselves to become experts in. So many only have expertise with certain brands, and that's going to limit your choice potentially in which robots that you choose for your applications. And due to the scarcity, there are often long lead times to these projects. So doing the integration project requires scoping, the design, the contracting, the actual implementation, which can lead to months of time between having the idea and being able to go live with something. So manufacturing needs a different approach. So to address those challenges that we started in the very beginning in terms of the need to be flexible, not only in the goods that you're producing, but also with flexibility around the staffing, that we need to fix these problems with the complexities in integration. So how we've addressed this at Ready is through what we call no-code cross-brand programming. So that means that through a new teach pendant or a touchscreen teach pendant running our software with a interface that works across robot brands, and with a style of interaction that is familiar to many of the operators that are already in your shop floor. And what this enables us to do is to democratize automation. And what that means is to allow more people to participate in the programming and operation of these robots and automated work cells. Cross-brand means you can choose the right robot for your application. There's a wide variety of choices, price points out there, and being able to select those based on those robots, vendors, different capabilities, gives you a lot of power in terms of having the right answer to the problems that you have. You can reduce costs from training. By doing more automation, you can add additional lines. With the lessened impact on programming, you can deploy more easily because you can do it on your own. Debugging or fixing a problem in a work cell becomes dramatically easier because more people can do it. We've heard many stories of having a lack of skilled robotics programmers that lead to more downtime because only a few people are able to fix a problem when it occurs. So the overlay on this is that by making it easier and more approachable, more people in the factory can interact with these robots, program them, and maintain them. So how you're going to see that in the demos today is through our software we call Forge OS. The application is called Task Canvas, but it's an operating system that's has a visual programming environment that you're going to see that can program many brands. You're going to see us demo the Yaskawa and a Fanuc. And it also enables you to interact and program the other devices in the work cell that need to be coordinated. So there's machine tools, there's laser scanners, force sensors that all need to be working together in concert to implement an automated task. And through the environment that we're going to show you, those components can also be controlled as well. From here, I'm going to pass it off to Kel Garen. Again, he's our CTO, who founded the company to solve this particular problem. So, Kel, take it away.
Absolutely. Thank you, Luke. And so I just wanted to briefly mention before we get into the demos, there's really two key features about this technology that address the issues that Luke has been talking about. The first is it's really a step function in ease of use. What this technology enables is that anyone on the factory floor can program a robot. Everyone from a high-level manager who might be interested in the data coming off of a system, all the way down to a machinist or a machine operator, even someone who's on second or third shift who might be fairly unskilled from a technology perspective, can actually program the robot and interact with the robot in the way that they need to. And we'll talk about that at length during the demos. If you could go to the next slide, Eric. The other key piece of this is the fact that it is cross-robot brand, that it is robot brand agnostic. As Luke said, one of the largest problems in the industry is the fact that every single robot is different. It has different interface, it has a different programming language, it has different buttons that you have to press. All of that adds up to that huge amount of differentiation in training to use these three robots that we see here in, for instance, a Fanuc, a Yaskawa, or a universal robot. The fact that our software basically makes all of those robots look identical and allows the operator to interact with those robots in an identical fashion and program those robots in an identical fashion means that you can pick the best robot for the job. If Yaskawa is making the best collaborative robot on the market, great. You can pick that robot for the task that you need. If you need a Fanuc because of the speed, or you need an ABB because of the speed or a specific feature that they provide, awesome, you can do that too. And you don't have to learn anything new. You don't have to re-upskill your workers to be able to interact with those devices. So that's really a game changer as well. It's the fact that this is cross-platform and that to the operator, the person doing the programming, where most of the time is spent, the robot underneath is the same. So we'll really dig into that in the demos. And so what you're going to see in the next couple of slides is our demos. These are machine tending tasks that we programmed. We pre-recorded these, but they were shot continuously, so you can get an idea of how long this took. So from there, take it away, Eric.
All right.
All right, so thank you for joining me in our test work cell here. And I thought what we would do now is dig a little bit further into how you actually use Forge OS to program a robot. So the robot I've got here is a Fanuc robot. This is a 710 IC50, but it's a large material handling robot, can lift 50 kilograms, commonly used for machine tending tasks, things like that. And the task that we're going to be doing is loading these rods into this lathe. Now, we're not actually going to put the rods in and machine the part just because this is just a demonstration, but we're basically going to go through the process of manipulating the part with the robot, putting it in the machine, taking it out again, and then dropping it in this outfeed tray here. So really, our core value proposition is about how to make the programming of this type of robot incredibly easy. I don't know if anybody has programmed a Fanuc robot before. It takes a while. It takes a lot of expertise and knowledge. You have to go on a training class. That's something that's a huge barrier in the manufacturing space. And we really want to make this type of programming as easy as possible. And in order to do that, we built a product called Task Canvas. And Task Canvas is what's running on this touchscreen. This is running on Forge OS, our operating system for robots. And then that is what is controlling this robot behind me. So let's start by looking at Task Canvas a little bit. So Task Canvas is basically a building block-based interface. So it's very easy to string together actions that you would recognize into actual robot programs. So it's not lines of code, it's not some script, it's things like move, open gripper, move on a grid, move to a pattern, things like that, that you would tell another person if that's what you were doing, right? Hey, I want you to pick that up there and move it over here, right? It's that easy. It's that level of kind of conversation that you're now having with the robot instead of lines of code, right? So the way that you do this is every block gets added into a flowchart. And a flowchart, something that we're all familiar with, you can have different blocks in the flowchart, and then the flowchart can branch depending on what happens in the task. And with that simple language, it's very easy to add blocks and make very complex behavior, right? So for instance, we're gonna just start by adding a couple of movements to the robot. So the way I do that is I actually just hit my 3-position switch in the back and enable the robot. And now I'm in a teach mode where I can actually move the robot around. And we have this very convenient panel down here for providing just simple robot motions, either with joints or in sort of XYZ tool positions. But I'm going to just start by setting the current position of the robot to as a waypoint, so that we're gonna move the robot there first. So I go here, I go to robot move, and now I'm presented with the move screen. And it's very simple. All I have to do is specify a waypoint. So I just click on that field and hit new. I pick the landmark that it's referencing. In this case, the base of the robot is where I care about. So the relationship between the base of the robot and the position I'm programming. So I hit that, and we'll keep using that same landmark for just everything we do here. Hit accept. So now I've got my movement. If I move the robot to a different position, let's say I move it backwards just a couple of inches, and then I go back to this task, click on that block and hit step, then the robot's going to execute that step of the program. Very simple. So let's move the robot in and into a position where we're actually gonna grab this part. The gripper is notched right here. So we just want to sort of center that over the part. So again, I'm just gonna move the robot in by holding down the position control button. This is moving in positive Z until the robot is roughly in the right position. So I'm a little high, so I'm just gonna tweak this just a bit. Down, just a tad, and then in. Just a little bit more until I'm right centered over the part. There we go. And now, before I save this motion, what I'm actually going to do is I'm going to go into our air panel, because the other thing that Forge lets you do that in a very simple way, besides actually program the robot, is any tools or devices that are attached to Forge OS become another thing that's very easy to program. So in this case, I've got this pneumatic gripper up here. There's 2 air ports that control whether or not it's open or closed. if I go into our end effector air control panel, I can just turn those air on and off and actuate the gripper right from here. Very easy. I didn't have to add any programs or scripts to do that. It's all just programmed through Forge. So I've essentially verified that that's a good spot to grab the part from. So I'm just going to open the gripper again. And I'm going to go back to my program, and I'm going to add another movement. So we'll move, set the base, accept, we're done. So now my motion, if I step through it, I've got my first movement back here, and my second movement, if I step again, where I'm actually centered on the part. Okay, so now what I'm going to do is I'm going to add a block for the gripper. So I go again into my blocks, go to Tools, End Effector Air, and I hit the state that is opening the gripper. And so let's see, I think it's this one. So now I'm actually have sent the air commands, turned the one air on and the other air off. That corresponds with the gripper closing. So if I step that, the gripper closes, so we're good there. And now I actually want to program the move that lifts the part up out of the tray. So I go back here again to Move, and now I'm just going to jog the robot to lift the part out. Now, it's a little, I don't want to bang up too much against the other parts, so I'm just going to sort of jog it up and back a little bit, just to get the sort of this nice diagonal movement here, just to lift the part out cleanly. That's a little too far. There we go, that's perfect. All right, so now I'm out of the tray. Again, save that as another block for movement. And now I want to actually pull the part back, right? So again, very simple. Add another move. Base coordinates. Now I'm going to jog the robot back to the position that I want it to be when it pulls the part out. I've got the teach speed set at about 25%, just because I was doing precise stuff in here. But if I increase this up to 100, now that I'm sort of far away from things that I don't want to bump into, I can move the robot, a good deal faster. Basically, at the maximum speed that it can be safely moved at in T1. So now I've got my waypoint. So now this is going to make it a little bit more interesting. So now I've got my waypoint. I want to get around to the lathe. But I know that I'm going to have some issues here because we're sort of in this interesting position where as I swing across, I'm actually going to cross over a singularity here. So what we want to do is we want to move with joints rather than in a linear space like we've been moving up until now. So I go back to my building blocks again. I've got robot moves, and I've got joint jump, and I've got absolute jump. So we're going to move the robot to a set of joint positions that are absolute relative to like the joint zeros rather than relative to where it currently is, which is another thing that you can do. And then I'm actually going to go back to the RCP, and I'm going to switch to joint move, and now I can actually move around the joints individually. So we're going to line this up as best we can here, and then I'm going to swing that joint that we were anticipating having a little trouble with around, and then I'm just going to get down here real quick and make sure that we're roughly lined up with the lathe. And that's pretty good. That'll be good for this demonstration. So now what I'm actually going to do is I'm going to go in, I'm going to say use current position because I want to move to the joints that represent where the robot is right now. And then I hit accept and I'm done. All right, so we've added our absolute jump to this spot, right? So now we're just going to simulate going into the lathe. And so I'll just add another move here real quick to actually move the robot and the part into the lathe. And again, we're just going to use, we're going to go back to Cartesian control now, and we're just going to jog the robot in. And we're going to come the other way, just a little bit. There we go. Now, I'm not actually going to put the part all the way into the chuck, just because of the amount of time that we have. But the idea would be is that I can very easily use this same interface to add subsequent moves that would put the part into the chuck. I can send a command to the machine through the same interface that we're using to send commands to the shunt gripper up there to close the chuck. One of the nice things about our software is because it's easy to control things like pneumatic tools and stuff like that, it's very easy to instrument older machines. So for instance, this machine is actually just has these 2 touch panels for opening and closing the door and a button for opening and closing the chuck. So we actually have products that we make which are just a pneumatic cylinder that can push the button to open and close the chuck. So you don't have to install anything, you don't have to change the wiring, you don't need a PLC, you just need our software controlling a little pneumatic circuit to open and close the chuck. And then the building blocks that you would create to perform that action are exactly the same as what you've been seeing so far. So it doesn't get more complicated, even though the robot becomes more capable, because now it has this machine tool that it can work with, etc. Right? So let me set that as a so we've set that as a waypoint. So let me now show you some features of Forge OS that make the rest of our program really easy. So let's say I assume I've now grabbed the finished part and I'm ready to pull it out of the machine. Well, a lot of the programming is already done for me, right? Because I know that I have this absolute jump up here that pulls me out of the machine. So I can actually just go into task canvas, hit copy from, and there's my absolute jump. Until now I have a second movement, and if I step through that, now the robot's going to come back out to the position that was at before. We could basically just sort of step ourselves backwards through our task to actually complete the rest of the task. So let's do that real quick. So I'm just going to switch back into joint moves, and I'm going to flip this wrist around one more time. And then I want this to be a joint move too, but I actually forgot to put that in. So that's not a big deal at all. So what we're going to do is we're actually going to move back to waypoint 6, which was the waypoint where we pulled this part out of here. So I just step that again. The robot will move there. And now that I'm at the position I want, all I have to do is go here and add another building block for that joint jump that I forgot to add the previous time. So using current position, this is the position I want to go to. So now I have a clean movement from the lathe back to the parts. And then I want one more movement that puts the part down into the outfeed hopper. So we're just going to add another move. And then I'm going to slow it down just a little bit since we're going to get close. And we're actually going to go in and program that motion. We should be pretty spot on because we came out of the previous, but not quite. It's all right. So there's our position. And that's where we want the part maybe just a little bit lower so that I don't drop it so hard. All right, so there's our position. All right, so now I've got that position there. I'm going to, instead of having to go and recreate the wheel again, I'm just going to go copy from. I'm going to go back up to my end effector air block there where I open the gripper, and now I just reverse the air signals so that it closes or opens instead of closes. If I step that, let go of the part, and I'm done. So let me really quick just make one more motion that moves the part or the robot out from the tray here. Just so that I get away so that I can make a complete loop here. And then what we'll do is we'll make a loop and then we'll step through this. And we'll find out if I made any mistakes. I think we're good, but what's nice about this software is it's very easy to debug things. You're never going to get it right the first time, but it's so easy to change stuff. Like you saw when we were putting the part into the lathe, I actually forgot the location that made it easy to sort of get back to where I was coming from. It's very simple to add it in, so you don't have to worry about making mistakes. programming these type of systems is complicated. We make an interface that makes it as easy as possible. So, all right, so we've got our motion here. And then what's really nice about this is to create simple logic like a loop, all I have to do, since this is a flowchart, is when I'm done with this block down here, this waypoint, I just want to go back up to the top. That's it. So all I do is I click on it and I hit connect to, and then I scroll back up to the top and go to my first waypoint. And now I have a loop. It's going to start at the top, go all the way down to the bottom, come all the way back up, and go and go and go. That's the idea. And there's other blocks that I could put in so that if you wanted to do it a certain number of times, or if you wanted to do it based on a sensor or some other input to change that logical flow, that's all super easy to do. So let's actually step through this again. All right, so this was our first waypoint, verifying the gripper's still open, which is nice before I go in and try and grab a part. I've got my part. There's the pull. And then let me just bump the speed up a little bit. We have our absolute joint move, which smoothly moves past this singularity, which is very useful for robots of this configuration. Got my motion that goes into the lathe, and then you could imagine all the other motions that are putting the part into the chuck, opening and closing the chuck, etc. My next step where I pull the finished part out of the lathe, right? And in the interim, I could have opened and closed the door, cycle started the machine, waited 20 seconds, etc. All of those are just other building blocks. Come back around. I've got my place position, drop the part, and I'm done. So in 15 minutes, plus or minus, we've taken a robot that really requires a solid week or more of intensive training to learn how to use through the native software that comes with it. And in 15 minutes, we've done the bulk of a machine tending task. As I said, the other things that you could add in terms of cycle starting the machine, opening and closing the door, handling sensors on the gripper, on the parts, whatever you need to do, those are all just extra blocks in our software. And the logic that lets you move between those blocks and actually build a program doesn't get any more complicated than what I just showed. So it's very simple to even do incredibly complex machine tending tasks with sensors, with multiple parts, multiple nests, machine tools that are either sort of legacy systems like this, where typically you'd have to install a bunch of extra hardware, but that's now easy because simple pneumatics solve 80% of the solution, all the way up to brand new machine tools, which we'll look at next, that are incredibly complex and require I/O signals and things like that in order to be used. So it's very versatile, but the core is that the programming doesn't get any more complicated than what you just saw, even though what the robot is connected to and what it's capable of can grow exponentially. All right.
So I hope you enjoyed that first video. Let me hand it over to Luke. I think we have a couple of questions that we want to address that came in while we in sort of the intermission here between our two demo videos.
Yes, perfect. So one of the questions we got was about safety. And Kel, the question is, how are you standing so close to the robot, and how do you program a robot in a safe way? I think it's good to touch on here quickly.
Sure, absolutely. So that the FANUC and most industrial robots that are not collaborative have a specific mode that they're in when they're in a teach mode. So it's called T1. And then there's a different mode that it can move at higher speed, and it's meant to be, you know, the door of the cage is closed. That's called an auto mode. So in T1, I didn't mention it in the video, but I've had to specifically move a key on the top of our touchscreen pendant into the T1 mode. And then whenever I'm moving the robot around by pressing those commands that I was pressing, I have to be holding down a 3-position switch on the back of the robot. So on the back of that pendant. So during that mode, when I'm in T1, anytime the robot is moving, I have to be holding a 3-position dead man style switch. And then once that program is done, I can turn the key, I can exit the cell. There's a safety circuit that knows that the door is closed and I'm no longer in the cell. I can then enable the robot in auto mode and run it at full speed continuously. That's also why I had to step through the program. I couldn't actually just continuously run the program because T1 doesn't enable that type of action. I can only step through the program. As soon as it's in auto, then I could crank the speed up, run the program full speed and in a safe way because I'm now outside the cage. The cage is secured. All of the other safety hardware is in a safe state, and I'm able to enter that mode, if that answers that question.
Great. And then I think somebody else just touched on real quick that we make the programming really easy, Kel, but how do we also make it easy to set up the I/O? Because the question is, how is the system configuration done specifically to make this so easy? Could you just touch on that briefly too?
Absolutely. So part of it is what we support. So through our interface, and there was another screen that you didn't see that we didn't really go through, that's basically a system configuration screen that lets you configure different pneumatic or IO-driven devices. But we support in our product offerings, we have pneumatic device support. In our sort of baked into our software, we support things like 24-volt IO. If you have a remote IO device, we support Ethernet IP, we support Modbus. So all of those different interfaces are sort of baked in. And then we have building blocks that you didn't see. For instance, like if there was a digital input that I wanted to receive from a sensor on the gripper that tells me I've actually gripped a part. There are sensors that you can buy for that 2-finger gripper that tell you exactly that go high from a 24-volt standpoint when I've closed around a part. So that input would just be another building block. And then in the generator for the building block, the screen that comes up when I create the building block, what you would see is you would see a drop down for all the available 24-volt IO. You would see a signal there, and if it was actually high, if the part was gripped, you'd actually see a little blue arrow that indicates that it's high. So it's very obvious what the state of the IO is. And then I would basically say, okay, when that building block when that sensor is high, I want that building block to follow the sort of downward path in the flow chart. If that building block and sees that IO is low, then it actually follows a different path. It branches off to the right-hand side rather than the bottom, and then I could connect building blocks to that, right? So for instance, in our program, if I wanted to check to see if I had a part after gripping the part, I could have had that building block in there that checked that IO. I wouldn't have had to add anything new. I would have had to wire it up, right? I would have had to actually connect the wires to the remote IO device, or we also offer like a simple breakout box for 24-volt IO that's super easy to wire in. So I would have had to do that physical wiring, but then once I do that IO is just there, and it can say, oh, you actually didn't grab the part because I'm not getting a high signal from that. And then I'd have a separate part of the program that's just more building blocks that is, oh, okay, maybe go back and try again, right, as a for instance. So because we have all of these common industrial interfaces, whether they're like field bus communication protocols or just simple things like IO and pneumatics, baked in, all of adding those capabilities and those features that depend on that IO is significantly simplified.
So there's a couple other questions. Let's hold those till the end Q&A. So I think it'd be great to continue on here, Kel, with the next demo.
Absolutely. So just really quick, I mean, this slide sort of differentiates what we're really talking about here, right? The old versus the new. The new is the idea that you have this modern touchscreen interface. It's something that is, takes all of the work that we've done over the last 20 years in terms of making computers and cell phones and all of that easier to use and made it available to an industrial application. Things like copy and paste, Things like being able to sort of create loops in your program just by connecting blocks together. Those type of modern affordances that you would expect in modern software don't really exist in these old paradigm interfaces. And again, as we'll show in the next video, I'll be playing with the Yaskawa instead of a FANUC. It's exactly the same software. Nothing changes about what I'm interacting with or the programming interface at all. So that's also the evidence of a really modern interface, is that it doesn't change, even though the hardware, including the robot underneath, might be different. So let's get into the next demo. We'll be doing a slightly more complicated machine tending task with a Yaskawa collaborative robot. And just to note, this is a collaborative robot now. So when I'm interacting with it, I have it in a mode where it's still in a teach mode, but this robot I can actually run continuously because it is designed intrinsically to be safe. If it were to bump into me or another object, it would stop. That is sort of the hallmarks of a collaborative robot. So just for the individual asked that safety question, that's why we're able to run this robot at a faster speed, as well as continuously, not just stepping through the program. So take it away, Eric.
All right.
All right, so we moved over to the other side of the work cell, and now we're going to talk about programming a few things that are a little bit more complex. So at this work cell, I've got a Yaskawa HC10 collaborative robot, and we're going to be doing machine tending. We're going to be tending these aluminum parts into this Haas VF2 mill. Now, again, we're just simulating this, so I'm not actually going to be running the machine or putting the parts in the vise. We're just going to be sort of putting them in there and then bringing them back out. And I've actually built out a little bit of a task to do, it's very similar to what we did over there with the FANUC, but basic loading and unloading, and then a couple of other functionalities that I'm going to walk through later on. But right now, I want to focus on one of the things that we end up doing a lot in machine tending, which is picking from a grid. And this can be something that's super time consuming because it really requires a lot of different robot positions. If you imagine I have this grid that's full of parts, I have to program sort of an approach and a pick for every single one. But we have a couple of functions that make it very easy in our software to do that. So I'm gonna walk through that. So in the task, we basically just have starting a block for turning on the air. So that's what I'm going to do. As soon as I contact the part, I'll turn on the air, which will turn on suction for these little grippers down here, and then I'll lift the part out. So I've got that building block to start. So before I go and actually turn that air on to create suction, I want to program the grid. So we have a building block in our software called grid, if I can grab on it. And this is a very easy to use user interface for specifying a grid. So I simply go through and pick sort of the number of rows and columns I want. So I'm picking a 3x3 grid of parts here. And then all I need to do to actually define the robot to move to all 9 of those positions is to define the 3 corners. So what I'm going to start by doing is defining the grid that the robot is going to be at when it's in contact with the parts, when it's actually about to pick them up with suction. So let's start by adding our first corner. So I'm just going to hit new. This is the same process that we used for adding waypoints back when we were talking about the FANUC. Set the base coordinates so that it's with respect to the base of the robot. And then I'm going to just use the robot control panel to jog the robot around until I am in contact with the center of the part. Now, I'm not going to be too precise here because this is just a demo, but I'm going to try as precise as I can because we want to make sure that the corners of the grid are as accurate as we can, because that accuracy is going to propagate to the rest of the parts. So I've got myself centered on this part pretty well. I'm going to move it just a little bit more. There we go. And then down so that the robot is in contact, and I've got a little bit of compression of those suction cups right there. Perfect. Okay. So I'm going to go back. That waypoint, that first corner, that one's done. So now I'm going to jog back up. And now I'm just going to jog over to my second corner, which is this guy right here. And the alignment between this tray and the base of the robot isn't perfect. It's not quite there, so I'm going to have to adjust this just a little bit. But it doesn't take too long. And then Just jog that a little bit longer. Perfect. All right. And again, push the robot so that it's in contact with the part. Get some compression on those suction cups so that I know I'm going to get a good pick. And then now I have my second corner. So again, I'm going to hit New, select the base landmark, and hit Accept. And now I've got my second corner. So again, third corner, same thing, New, base coordinate, and I'm going to jog up again. And now I'm just going to increase the speed just a little bit and move the robot over to this other spot, that other far corner. And then now that I need to be a little bit more precise, turn down the robot speed just a tad, get roughly lined up here. And then get closer to the part so I can see what I'm doing. Just a little tweak there. That's pretty good. All right. So again, we want the robot in contact with the part with some compression on those suction cups. And there's my third waypoint. So now I've got all three waypoints that define the three corners of this grid. And I'm going to set my speed. Speed's still at 10%. That's how fast the robot's going to move to each of those points. And I'm going to hit Accept. So what's going to happen is, as this graph executes, as the flowchart moves from block to block, every time that this block is visited, right, every time the execution hits this block, it's going to go to the next point in the grid. And it's going to keep track of that itself. So what's useful about that is, right now I've programmed just the positions where I pick up the parts, right? But if I tried to go from here down to that position, I might, especially for like far points like this, I might, you know, kind of slide into the part. I really want to approach it from directly above. But each part has its own position that I have to approach it from directly above. And that's what is typically so time consuming about this process, is not only do I have to program all of the picks, I have to program above all the picks. Well, our software makes that super easy. So all I need to do is go in and copy this grid move. So now I actually have two, right? So we know this is where I am going to actually grab the part with air. So this is the block that I want to be where it's actually in contact with the parts. And I've got this other block now that's a separate grid where I know they're the same parts right now because or the same positions right now because I just made a copy. But what I can actually do now is I can go and just modify those three corners. And since I already know where I am, and I already know that those 3 points are, you know, they're pretty close to where I want to be, then I can actually do this rapidly. So let's first jog the robot away from the part a little bit. And I'm actually just going to remove the parts entirely because I know that the robot, I know that the positions against the parts are already done, so I don't really need to know that. And I'm just going to move the robot directly upwards when I program the new ones. So let's start by, so we have our first direction here, which was that corner that we're currently at. So if I hit move to, I'm now at where I would have been if I was picking up that part, right? I go into the RCP, and I change our mode from jog, which is where I've been just moving the robot around, to jump, okay? And jump just lets me move a set position away from where I currently am in a direction. So let's pick 2 inches. So I'm gonna move the robot up 2 inches, pick the up direction, and then hit execute jump. So now I've moved the robot up 2 inches from where that waypoint was, and I can go back into this waypoint and just add a new one, right? I can just overwrite that previous waypoint in this grid move. Now the other grid that I did before, that one's unchanged, so the position where I'm in contact with the part is still going to be fine, but this waypoint is now going to be above the part. And I can do the same thing for these other waypoints. So I move to, the robot will move to the pick position. I remove the part, so I'm not worried about scraping the suction cups against it or anything. I go back to my RCP, execute the same jump again. It moves up 2 inches, and now I add a new waypoint there. Now I do it again. Move to the third position, again, where I'd pick that third part. Jog the robot up again, and add that as a new position. And then hit accept. So now I've got a grid of positions that are above these 9 parts. a grid of positions that are in contact with those 9 parts, air so that I actually grab onto the part, and then I need one more block so that I can move the part directly up. I don't want to just start moving when it's down inside its pocket. I want to move back up to the approach position. So all I do is copy from that first grid move. Okay, so now that we have our 3 grids, the grid where we're approaching the parts, the grid where we're actually grabbing onto the parts, turning on suction, and the grid where we're lifting the part up out of the tray, we can actually step through this. So I'll step through the first position, step down, pick up the part, and step up. Now, that same sequence as I step through this program will actually happen for all of those parts. And I can actually demonstrate that real quick. So if I just turn the air off for this, put this part down, since I've already stepped through these 3 grid moves, if I step through them again, they're actually going to go to the second point on the grid. So if I step again, we'll go over to the second part, step down, grab it, and step up. So it's not, what's nice about this practice of defining grids with this tool is, for a grid like this where I only have 9 parts, if you were having to program each part individually, it wouldn't be a huge amount of time. But you can imagine if I have 30 parts or 100 parts, let's say my parts are much smaller, that time adds up a huge amount. And no matter how many parts you have, in this interface, you'd still just be defining those 3 corners, and then for the approach grid, modifying those 3 corners. So it really would have taken about the same amount of time, even if I had had 10 times the number of parts that I had to specify in this grid. So now what I want to do real quick is, now that we have this grid motion where we actually go down and pick each part, let's talk about the rest of the program that I had created here. So we basically have 3 other sections of the program. Now this, we didn't talk about this yet, but this is what's called a container. So it's basically a part of our program that we can make a isolated block that you can save, you can import it into another program, whatever you want to do. You can make a copy of it, you can paste it elsewhere in the program, whatever you need to do. But it's a nice way to just take, you know, a sequence of motions that we've made for actually getting the part into the mill and sort of truncating it down so that it's just a single block. So essentially I have a container for loading the part into the mill. We're just going to, again, set the part in the or on top of the vise. I have a block where we're going to run the mill, and running the mill, we're going to get into a little bit about our digital output capabilities, because our system has the ability not only to control air, but also to control any kind of 24-volt I/O systems, so digital inputs and outputs, registers, things like that, Ethernet IP, Modbus TCP, things like that, that are these commonly expected interfaces. When we talked about the lathe, we didn't talk about that because it's an older lathe that you might just use pneumatics in order to interact with the machine. This Haas mill actually is set up with these digital inputs and outputs. One for cycle starting the machine, so the machine will close its doors and start an operation, which is it's just going to sit there for 5 seconds and then open its doors back up. But then it's actually going to send a signal back to us that the robot can wait for and catch, so that the robot doesn't go and try and pick the part while the doors are closed while the machine is running. So it's this conversation now that the robot is having with the machine tool with just a few building blocks. Again, very easy to set up, very easy to wire in, and then which makes this system much more capable with this modern machine tool. So let me actually run that, and we can talk about it while we're going here. All right, so I've got my. Oh, the other thing we want to do is we want to do this more than once. That's sort of the point, right? So something that we can do really fast is we want this program to basically be a loop. So all we do is we click on the bottom building block, hit connect to, and go to the top building block. And that'll actually make this so that it goes over and over again. As I said, every time it cycles back through, it'll go to a new point on the grid and we'll pick up a new part. All right. So I'm going to start by moving to the first part, pick it up, and then this is where that sequence of action comes in that I pre-programmed, where the robot is actually going to go deposit the part in the mill. Now, if we were really machining, obviously I'd put it in the vise, I could also actuate the vise pneumatically. Both of those vices in there, one's a shunt and one's a Kurt vise. Those can both be actuated pneumatically. Our system provides that type of action, so all of that is being run by our system as well, so I could open and close the vices. Once the machine is done, it's gone through that cycle, the robot is signaled to pull the part out, and you put the part into a bin. And all of this is being driven by our building blocks. There's nothing going on here besides the activity that we programmed and then the cycle that the machine, the mill, is running when we tell it to cycle start. That's all that's going on. So everything that you see here, besides the mill's program itself, we programmed in Forge with these building blocks. So that's really the idea, is it's a powerful interface not only for doing simple pick and place tasks, but tasks where it's a not so simple pick and place where you have a lot of parts to handle. It's a lot of things that you traditionally would have to program point by point that you now can use our sort of convenience functions like grid picks. We also have patterns where you might have a series of waypoints where they're not on a grid, but you still want to visit them sequentially. And then also interaction with machine tools, using pneumatics for the vices in there, 24-volt I/O to talk to the Haas, or more complex field bus protocols. Really anything you need to be able to not only program the robot and its actions in an easy way, but also program all of the different peripherals that the robot has to interact with. The suction grippers and pneumatic vacuum generators that are on the end of the robot, the mill, any sensors that you might have. Right now, this isn't any sensor driven, but if I had a sensor that was detecting whether or not I had a part, that could be represented in this program as well, and I could change the flow chart so that if I had that sensor and I didn't find a part, I could go back and try and pick it again, or maybe I alert the operator because something's not right because there's no part in that spot, etc. So with this simple tool set, you can really build complex behavior very easily. Our motto is sort of like, it's the rule of twos, right? In 2 minutes, I can do something with the robot. I can move it around and really program it. In 2 hours, I could program something that is almost as complex than this. And in 2 days, I feel like I'm an expert because it's really a simple set of tools you have to learn. And then once you do learn that, nothing gets more complicated. Now, you have to do more operations, right? There's a lot of blocks. There's a lot of things that this program is doing, but each one of these are the same level of difficulty, right? So even though the robot becomes more capable, it's dealing with machine tools, it's dealing with sensors, it's dealing with vices and actuators and suction, how you program it and how you interact with it is staying the same level of complexity, which is easy. So that's really the power of our software, is being able to rapidly build out complex tasks like this that have complex logic. They otherwise would be very difficult to program because it's a lot of waypoints to program, and interact with machine tools seamlessly. So, all right.
All right, thanks, Kel, for that demo. We got a handful of really good questions as that second demo is going on. We're going to save those and dive into those at the end of the presentation. Right now, I'm going to spend a few minutes sharing some real world examples of Forge OS kind of in action. So first of all, I just want to note that Ready right now is supporting manufacturers of all sizes, from small manufacturers to enterprise. And we're working with manufacturers in a number of verticals. Everything you see on the right are some of the companies and verticals that we're currently working with. The case studies that I'm going to talk you through happen to be mid-market manufacturers. So AliCat is an interesting one. AliCat makes mass flow meters and mass flow controllers, which are used in ventilators. And so they had a problem in that demand was increasing, but they'd hit a wall with hiring. They couldn't hire reliable workers for the third shift. And then layer on top of that, skyrocketing demand due to COVID-19. And so AliCat had to increase beyond their maxed out production, and they had to do it quickly without pausing production or with a limited pause to production. So they needed a solution that could be implemented quickly by their own people. One kind of additional complication is they had no robotics experience. So the solution for them was a forge-powered automation solution. They did a bunch of digging into robot OEMs, integrators, and decided that they wanted to own the automation on their own. So their complete hardware package, which included robotic arm, gripper, base, would allow them to deploy rapidly and own the automation moving forward. So that meant they could troubleshoot on their own, they could program for changeover, and then they could rapidly adjust to meet opportunities. So the results of this particular implementation were pretty profound. So with no outside support, AliCat received, trained, programmed, and deployed on their own in 3 days. And again, this is with no robotics experience whatsoever, and not even so much as a phone call to Ready Robotics. They were at lights out in 10 days, and this implementation instantly boosted the output of a critical component by 74%. So this would have been a choke point. Instead, AliCat was able to ramp up production significantly, take on projects or jobs that they would not have been able to take on, and they achieved full ROI in under 30 days. Now, for what it's worth, that speed to ROI certainly is not standard, but it just goes to show the potential of Forge as an automation solution. Another case study I want to share really quickly is a company called Harmonic Machine. So Harmonic Machine is a supplier of precision machine parts to commercial transportation and oil and gas. They, like AliCat, were running at maximum capacity. They had new growth opportunities with core clients, but they couldn't achieve those by running just 2 shifts. So the problem with them came down to the 3rd shift. They couldn't hire reliable machinists for that 3rd shift, and so they were limited. They also had kind of the added challenge of frequent changeover between jobs. So in their world, every 3 to 5 days, this machine has to be updated, or the cell has to be updated for a new job, for new parts. And so they needed to be able to manage frequent changeover. They wanted to own automation on their own so they could program the tasks and then quickly switch between tasks. And then also kind of critical for them is, given that they're running at maximum capacity, they couldn't afford to be down for days or weeks if there was any sort of an issue. So they needed to be able to really own the automation so that they could manage troubleshooting on their own. So again, in their case, they chose a Forge-powered automation solution that enabled them to program automation themselves. The responsibility for this fell onto a newly hired machinist who had no robotics experience. So this is not a 30-year industry veteran who'd been around automation and been around robots. This is somebody who is just completely fresh to robotics. And the result was this guy, Jared Kuva, really smart guy, found Forge OS intuitive enough that he was able to program. In their case, it was under 2 weeks that they were fully programmed in production. And a big component of that was, in addition to just programming tasks, was building a custom end effector for their robotic arm, building a jig for parts alignment. So there are a handful of things that went into this. But they had their system up and running within a couple of weeks. And I think one of the important components of this particular integration or deployment was that they now have multiple people on their floor who are comfortable troubleshooting the robot and managing changeover. So not only are they able to run that 3rd shift, so they're 24/6, 24 hours a day, 6 days a week. They've been running for over a year, lights out with no issues. But there are multiple people during any shift who can interact with the robot, manage changeover, and troubleshoot if there are issues. So in their case, a few kind of highlights. They did deploy with existing staff and no experience. They accommodate more than 20 jobs with this particular cell and this robot, and easy changeover on demand with no interruption to production is kind of key for them. They're at near 100% utilization, and this is primarily due to fast changeover enabled by Forge OS. And as I mentioned earlier, they're lights out with no issues. So their system has been running 24 hours a day, 6 days a week for over a year with no issues. So these are a couple of examples of, and I think speak to how easy Forge OS truly is to deploy and manage, even without robotics experience. And now we've got some time for Q&A. So I will let Luke kind of manage the questions from here. And then we've got just a few kind of closing slides once we get through the questions.
Great, thanks, Eric. Just be mindful of time. We're gonna give some short answers to these questions. My contact information will be at the end of the presentation. There's a few questions in here about how we actually engage with our customers, and I suggest that you just reach out to me directly, and I can answer those types of questions if you have them. So the first question was around, can the robot be programmed on a PC initially and then load the skeleton program in the Forge pendant? We do have the capability for some sorts of tasks, such as palletizing, where those can be developed in a wizard. And then those tasks are loaded into the interface that you just saw, where they can be interacted with. And also a future feature where there are other software programs that allow you to do more advanced simulation, mainly for more kind of process tasks or welding, that will enable those kind of tasks to be loaded into the Forge OS as well, so that you can do the final test and touch-ups as needed when using those types of simulation packages that enable that type of offline program. There's a question about if you already have some sub-programs on the robot, can those be called from Forge OS? And the answer is yes. We have a block that we call the native block, which enables those sub-programs to be referenced from a task canvas program. There's a question about creating sub-programs. As Kel showed towards the end of that last demo, the concept that we have is called a container. And in that container, you can put the same building blocks as Kel was showing in the demos. You can put them together in that container. There is one way to do it, and the other way is to create what we call subtasks. And subtasks can also be run in parallel as long as it's not controlling the robot motion. So if you have a need to control some other I/O at the same time as the robot is moving, then those can be put into a task, and you can have reusable code in that way as well. Next question is, how do we control different robot brands? So one of the things that we've done, invested a lot of effort in, is creating a layer, a common interface to robots. We have a software development kit that enables robot brands to integrate to Forge. And that is then done through our software is running on an industrial PC that's connected to the robot, in most cases over an Ethernet connection to the controller. So the combination of those two things is how we're able to control many brands through our one interface. There's a question about collaborative robots, that one of you was familiar with being able to move a collaborative robot around in guide mode. So if a robot has that mode, that can still be used to position the robot. So Kel was demonstrating with the jogging function to move the robot around, particularly on the non-collaborative robot. But if a robot supports guide mode, you can also hand move the robot into those positions to then record the waypoint. There's a question about connecting with PLCs or vision systems. And we have a recent social media post with a vision system that is integrated out of the box with Forge. And it was on that same robot that you just saw, where that vision system is able to be configured directly in Forge, and then that vision system is able to provide those waypoints based on where it sees the parts should be picked up. So I encourage you to check that out in either our LinkedIn or Instagram or Twitter feeds, and you'll see that video of how exactly we're doing that vision-based picking using that integrated camera system. And the last question is, how long did it take to change over the system for these different tasks? So changeover is a matter of really what you saw there. So if that part size, let's say in the second case, say the part size became larger, so that you now had less parts in a grid, you would go through that same exercise that Kel did, where he programmed those 3 different grid of the position of the parts and then the approach points. So it's literally in the order of minutes. So that would be on the order of that demos in 15 minutes. So changing your tray and the parts and doing the programming. And Kel didn't show the entire piece of programming the approach in the machine, but in the matter of tens of minutes, an hour, you could be reprogramming that task and be able to be back up and running. So it's as quick as what you saw today to be able to change to a different part. And let me just scroll through here. I think I got all of those ones. So, so if I didn't answer your question, or if you have more questions after the talk, again, my contact information will be coming up here, and I encourage you to just reach out to me directly, and I'll be happy to either answer them or get you in contact with people at Ready who can answer it.
Awesome. Thanks, Luke. So just a couple final slides here. One thing that I wanted to share with everybody are a few Ready resources. So at readyrobotics.com, there's some good content for people that are either currently deploying automation or interested in getting into automation. So one thing that we built and shipped pretty recently is a robot selector. It's basically a library of every 6 degree of freedom robot we could find. There are over 750 of them. So we're in this unique position since we're brand agnostic, where we're not tied to a particular brand. We're able to create value, I think, by building this library for anybody to search. So basically, search by brand, search by payload, search by reach, collaborative or industrial. You can find it on our site under the resources and tools section, but that's a pretty useful tool. And then also within our white papers, we've got, Luke has mentioned them kind of throughout the presentation. We've got a lot of really good information and content about deploying automation, about no-code programming, about how software can reduce deployment costs, how to avoid pilot purgatory. There's a lot of really good content there. So feel free to check out our white papers and our articles. Hopefully there's something there that can help with your next deployment. And with that, Luke had mentioned, if you have follow-up questions, if you want to talk about a specific deployment or your specific situation, or you have specific questions about Ready products, how we might be able to help with your output, uptime, OEE, please shoot Luke an email, as the email is right there in the slide. And that's it. Thanks for joining us today. I mean, we obviously are huge believers in what we're building. We think no-code, cross-brand robot programming really has the potential to unlock the next great industrial revolution, and we're excited to play a part in it. And hopefully, we get the chance to work together with you guys as we're following this path and unlocking automation.
That's great. Thank you, Eric, for hosting, Kel for the demos, Kristen from Automation Alley, as well as Tom Kelly for organizing this. We appreciate the fact that everyone here took time out of their day. We know everybody's busy, so greatly appreciate having the opportunity to present this information to you. And like I said, please contact me if you have any questions. And once again, thank you to our excellent hosts at Automation Alley. And everybody have a great day. Thank you very much.
Thank you, everybody, for tuning in. Now we're going to do the circle of thank yous, right? I just want to give a huge thank you. Eric, Kel, Luke, this was absolutely awesome. It's one thing to hear, oh, it's easy to code. It's another thing to see, I have apps on my phone that are harder to navigate than that OS. I mean, that is absolutely democratizing accessibility. And that's what's going to force that next industrial revolution. So we are right there with you. I thought it was fantastic. You guys take advantage of Luke's offer to reach out. He's super accessible. He's really great. A wealth of technical information. Check out their website. Their white papers are awesome. Again, it's ready-robotics.com. The one thing I want to share with you is a little bit about something that Luke had reached out with. Oh, as my lights go out here, let me scroll over. Luke reached out at the beginning of the COVID crisis and gave us an offer to offer their Forge OS system at no cost to Michigan manufacturers during that crisis to offset those worker shortages. And that is such a testament to their commitment to doing good for communities and people. And that's that thread that carries through everything that they do. And those are those companies that we really want to give opportunities to highlight. So I thought this was a fantastic opportunity for you guys to see how easy it is and really figure out how accessible it's all going to be. Thank you to everybody for tuning in. If you're not familiar with Automation Alley, we are the World Economic Forum AmHub for North America and Michigan's Industry 4.0 Knowledge Center. We do these tech takeovers. Thank you, John. We do these tech takeovers most Wednesday mornings. We also have a variety of digital content. And I just want to give everybody a shout out. Next week's Tech Takeover is from Ascent Aerospace. They're a leading provider in aerospace tooling systems, factory automation, integrated solutions. They're to date one of the coolest facilities I've ever been in. I've never stood by a plane wing. I felt like a tiny little ant person. It was amazing. And so theirs is going to be on flexible robotic solutions, drillers, end effectors, how to define the right size robotics for your application. So again, we do these most Wednesday mornings. Definitely sign up. You can register at our website, automationalley.com, for any of our digital content. And we look forward to seeing you back next week. Thank you guys again. Have a great day.